Hello, everyone. I'm Wei Wei from Microsoft Research Redmond. Today, I'm very happy to give a topic review of data center networking session of SIGCOMM this year. So let's start with the context first. What is a data center? A data center is a facility used to host computer system and associated components such as power, cooling, telecommunication, and storage systems. So to some degree, you can think data center as a server room, but data center is super large. So to give you some sense of the physical size of data centers, so I borrowed this figure from my colleague Dave's talk last year. So this is architecture rendering of one of our production data center buildings. So know that we don't really use, we don't really put any, 747 in our data center. So don't worry about that. But these two 747 give you some sense of how large the physical space is. That's why a production data center can easily host tens of thousands of machines. So given the trend of cloud computing and digital transformation, many companies are building a lot of data centers around the world to provide service to global users. So for example, the Microsoft operates 61 regions around the world, and each region has multiple data centers. So we can say that the data center is one of the most important infrastructure for our daily lives. So now let's look at the network interconnecting the server inside the data center, which we call as data center network. The data center network typically uses a cloud topology to interconnect machines. So as shown in the figure, so the bottom green ones, they are the servers. So on the top of the server, there are 4 tiers of the switch: top of rack, leaf, spine, and the regional hub. So server under TOR switch form a rack, and server under the same set of the leaf switch form a cluster. Server under the same set of spine switch form a data centers. So a region interconnect multiple data centers through the regional hub switch, which is on the top. So compared to the internet, data center network has the following characteristic. First, it is the perfect single administrative domain. That means operators have full control of the network elements, such as the switch, NIC, and part of the end host, such as the hypervisor. Second, data center network has some very unique network properties. The round trip delay is very small. The bandwidth is pretty high. The switch buffer is very shallow. The traffic is bursty, and there are multiple equal cost paths between two servers. Third, since data center carries so many important workloads that can directly impact our daily lives, operators have very strong motivation to improve the reliability and the performance and reduce the cost of data center networks. So this characteristic enable many innovation opportunities. For example, software-defined networking, network function virtualization, smart NIC, programmable switch, kernel bypass networking such as DPDK, hardware transfer offloading such as remote direct memory access, reconfigurable network using the optical circuit switch, and specialized network for AI, HPC, and these aggregations. So all this hot technology are first adopted or heavily adopted in data center network environment. So I would like to say that the data center is the perfect environment to incubate and evaluate new networking technologies. So in this year's SIGCOMM, so we have this data center networking session, and there are 5 very exciting papers. The first paper is from Google and University of Michigan. So this paper is about RPC performance. So we know that RPC generates the majority of the data center traffic, so its performance is very critical. But the network overload has huge impact on its performance. So in this paper, the author proposed Equitas to provide RPC network latency SLO for selecting important RPC. So it has two main ideas. First, it leverages weighted fail queuing, which is widely supported by commodity switch, and align the priority class with weighted fail queuing QoS level as the granularity of the RPC, rather than application. Second, it explicitly managed RPC and made among different QoS levels using a distributed AIMD algorithm. The second paper is from CMU, MIT, and UC San Diego. So in recent years, there are many promising proposals about reconfigurable data center networks using the optical circuit switch. So reconfigurable data center networks, they can provide very high bandwidth with very low cost. But for each pair of the hosts in the network, so the reconfiguration data center network will create multiple time division paths with very different bandwidth and latency. So such kind of drastic variation in network condition really confuse existing TCP variants. So to solve this problem, the author proposed time division TCP for reconfigurable data center networks. So this work has two main ideas. First, it keeps independent congestion state for each distinct time division path. Second, so after a circuit reconfiguration, so the TCP will leverage the network support to receive the notification of the path change, and then quickly match the local view to the current path. The third paper is from TU Berlin, Princeton, MIT, and ETH. So as I have mentioned, the shared packet buffer of data center switch is a scarce resource, and it has huge impact on the performance. Actually, with the increase of the link speed, the buffer per port for GPPS keeps decreasing. This means we really need a good buffer management solution for the data center switch. So in this paper, the author proposed ABM, active buffer management. So compared to existing work, ABM accounts for both total buffer occupancy and queue join time to achieve per priority isolation, predictable both burst tolerance and high throughput. The first paper is from Cornell and Waterloo. So this paper targets at a very, very classical topic named high performance data center transport protocols. We all know that we always need data center transport protocol to achieve high throughput and low tail latency. So in this paper, the author proposed a new transport design called data center parallel iterative matching. So this is a proactive receiver-driven transport that can achieve near optimal performance only using commodity hardware. So as the name suggests, this work revisits PIM, a very classical scheduling algorithm for switch internal fabric scheduling. But the data center is very different from switch internal fabric. So the author conducted new theory analysis of the PIM protocols for the data center network context. And based on this new theoretical analysis results, the author extended PM design to overcome challenge introduced by data center networks. The last paper of this session is from Google. So as we have mentioned, today's data center network typically use cloud topology. Of course, cloud topology has many advantages. For example, the good fault tolerance, high throughput, high bisection bandwidth. But cloud topology is difficult to incrementally upgrade and refresh because we need to rebuild the spine layer. In this paper, The authors share their unique experience to evolve the Juniper data center network from a traditional cloud topology to a direct connect topology among the machine aggregation blocks. To this end, the author used optical circuit switch to build a reconfigurable data center interconnection layer among the blocks. The author also designed corresponding traffic and topology engineering mechanisms. So this is the end of my presentation. Thank you for your listening and hope you will enjoy this very exciting session.